Sputter deposition of molybdenum disulphide coating. Now, this molybdenum disulphide or say tungsten disulphide, these are the materials which we can put in the form of this formula Mx2, and where this M stands for one element of this transitional group, and these sulphides are known to have very low coefficient of friction, or in other words a super lubricity. So, these materials are known for their super lubricious property. Now, how this super lubricity is obtained? Now, to look into this issue, what we can see, this is actually MOS2. That means, it is as if it is S, M, O and S. So, when we like to see its structural formation, we can see that we have a hexagonal array of this sulphur and molybdenum. So, this is actually one plane containing the sulphur in an hexagonal array, in an hexagonal arrangement, and just with it, adjacent to it, we have another plane, and this plane is actually the plane containing molybdenum. This is also in hexagonal array. So, that means, here we can show these lines, and finally, what we have here, another plane that is containing sulphur. So, this is one set of MOS2, and below that what we have, further to this we have again here another plane containing sulphur and followed by molybdenum and sulphur. So, this is one set, this sulphur, molybdenum, sulphur, then also we have sulphur, molybdenum, sulphur. So, what we find normally, that the bond between this molybdenum and sulphur, that is a covalent bond, that is very strong. However, the bond between this sulphur and this adjacent sulphur, which is from another MOS2, that set, this bond is rather weak, and also this distance, this interatomic distance, that is more than the interatomic distance here between two sulphur planes. So, this distance is actually high compared to this distance, and this force between these planes, that is a very weak force, and that is actually van der Waals force of attraction, and that is weak force. So, when a force is very much acting on this plane, then this sulphur molybdenum bond, that does not break, but the bond between these two being the weak. So, this plane can easily slide over this one, and that ultimately results in a very low value of friction, and it is exactly what we know as super lubricious property of those materials like molybdenum disulphide or tungsten disulphide. Now, here what we can see, two planes are there, basal plane and H plane. These are to be taken into consideration, because the orientation of this plane is extremely important to have a very low value of friction, low value or high value, good performance or poor performance, this too will depend upon the very orientation of this basal plane or this H plane. Now, let us look what is meant by this basal plane and H plane and how they should be oriented. Now, what we see in actual field of working, say this is one substrate, it may be made of just a low carbon steel C20 steel, and we like to deposit a coating of molybdenum disulphide over this. So, it is just not a coating of MOS2, it is just not MOS2, but it will be MOS2 with right orientation, and if we can't get this right orientation, we may not get a very good value of coefficient of friction or a what we call super lubricious property. So, this is very important. So, let us look what does it mean if we put this hexagon like this. This is one way of showing. This is one way of showing. So, that means here this axis, what we call C axis, that is perpendicular, C axis is perpendicular to the surface of the substrate. So, this is one situation. So, this C axis is perpendicular to the substrate, or we call it basal plane. So, here two things we must take notice of, those two things. One is basal plane is parallel to the substrate surface and obviously C axis is perpendicular, but we can have another extremity. So, another extremity means this way. So, let us have a quick look here, that this is another situation. Okay. So, this is here what we see, this basal plane, this plane. Now, this is no more parallel to the substrate surface, but it is perpendicular. That means, the C axis is now parallel to the substrate surface, and this is actually the H plane, and that is now parallel to this surface. So, this is one of the extreme worst situation, under which condition what we can have a very poor performance of this coating. Now, this can be, so here we can summarize one thing, that even to have this coating, whether it is PVD or any other process, first and foremost thing is that whether this basal plane is parallel to the substrate surface, because only in this direction as it slides here in this direction, then only we can expect good coefficient of friction, and if it is perpendicular like this, then this sliding will not be easy, rather sliding will be difficult, and with result of high value of friction, high sliding force and removal of the coating. Another thing also we can look here, that this normal orientation, say we have the substrate here, and these are this is just the arrays of coating. So, if this is the orientation and then these are the basal plane is like this. So, then there is also attack from the atmospheric oxygen, and that can also damage the coating. So, when this H plane that is parallel to this substrate surface, in that case also we can have oxygen attack in this way. That means, here the attack will be difficult, but here it will be attack will be rather easy, and in this way the atmospheric oxygen or humid atmosphere, the moisture can get in, and then it may cause deterioration of the quality of the coating. So, then under the action of this force, this coating will immediately break, and that will lead to high value of friction. So, this is what we call basal plane and H plane. Now, we have type 1 and type 2 structure. So, type 1 structure, what we can call, we can refer to this previous figure. That means, if we have the basal plane parallel to the substrate surface, then we call this is as type 2 structure, type 2, and when the basal plane is perpendicular to the substrate surface, we call it type 1 structure. So, obviously, our choice will be type 2 structure, considering that low value of friction is most desired, and this is for the purpose of having the best performance of any component or wear part. Now, what we can see further to this, sputtering of molybdenum disulphide. Now, this MOS2, what we have written MOS2, this sputtering is possible by at least 2 processes, because this is not a very good conductor of electricity. That is why earlier this DC sputtering, that was not very popular, and what we had, it is mostly RF sputtering, RF radio frequency sputtering, and we know that with this RF it is possible to use a non-conductor or a poor conductor as one of the target material. So, it was a RF, but RF has a complexity that is also noted, that it is the complexity of matching the capacitance with an external capacitor, and it is also the impedance matching. So, that is why later on came into being what we know as mid frequency pulse DC. It is actually mid frequency pulse DC sputtering. So, both are very useful in having a coating of molybdenum disulphide on a substrate, and in this case it is mostly for all mechanical application. It is going to be a steel substrate which can be coated with this molybdenum disulphide to have better performance in all tribological activities. Now, here the sputtering of molybdenum disulphide, we can take a solid target of MOS2. However, the question is that during sputtering, when this material is coming like a flux and intercepted on this side by the substrate. So, this is actually the substrate and this is target. So, the question is whether we get here also MOS2 or it is MOSX, where x is less than 2, and if it is less than 2, is there any problem associated with the value of friction. So, these are the few things can be also noted for this sputtering operation, and at the same time there is another way of doing. So, this is applicable whether it is RF or mid frequency pulse DC sputtering, and in this case definitely the parameters which are going to influence this value of x, that is, on one hand we have the cathode current. So, it is actually the cathode current, that is the set value of cathode current. This is number 1. Number 2 is also the process pressure. Process pressure, that is also another parameter. And number 3, what also appears to be quite important and it can also influence, that is substrate bias voltage, substrate bias. So, these three, this combination is very important. Their selection of this and their combined effect can lead to a particular value of x, and not only that, it can be also this formation of this basal plane or H plane. So, this is what we can mention here. So, when it is the basal plane, so from this XRD, X-ray diffraction diagram, we get a peak of 002, and that is a confirmation, of the existence of this basal plane, which is given by this 002 orientation, and that is parallel to the substrate surface. It can be H plane, and in that case the peaks comes from this 111 or 110, and for that we have definite angle 2 theta, and from this, from the standard XRD corresponding to this MOS2, we can find out the value of theta, which corresponds to this 002 or 111 or 110, and from that, concerning the quality of the coating, we can have fair idea, and whether it is the effect of high cathode current or wrong choice of process pressure or the substrate bias selection. All these things can be known just by looking at here, that whether on the XRD diagram which peak is coming up, and depending upon the sharpness of the peak or the little widening of the peak, from there also we can have fair impression about the size of the grain, fineness of the structure, apart from scanning microscopy. So, these are the few things one has to look while going for this MOS2 coating deposition, because ultimately it is going to be one aim that it is the best possible mechanically functional coating. So, from this XRD we can get a fast information and very preliminary information, but it is very useful in that whether we are in the right track or right direction in the whole deposition process or deposition activity, and whether the process parameters selections are proper, which may finally lead to one of the best performing coating. So, this is one thing one has to look, but apart from this, it is also possible, just instead of using a target which is made of MOS2, what we can also do, it is also called reactive sputtering. Reactive sputtering. So, in that case we have one molybdenum target, and then we have one substrate facing this molybdenum target, and here just like reactive deposition by sputtering, say for example titanium nitride deposition or aluminum nitride or chromium nitride, or even it is molybdenum nitride, but in this case it is going to be molybdenum disulphide. So, MO flux, sputtered flux will come in this side, it will on its flight towards the substrate, and then what we have here incoming, instead of nitrogen it will be H2S, that is the source of sulphur, and then this MO from this target and this H2 from H2S from this external source, that can also make this finally MOS2. This is also possible, and in that case perhaps this problem of less sulphur in the coating here. So, this is on the substrate, that means less sulphur, deficiency in sulphur, that can be eliminated by this reactive sputtering. So, that is also possible. Now comes coating architecture. What we want? We want a stable coating, and this stable coating means it should be stable not only in a very restricted atmosphere, that by that what we mean, that it should be high vacuum. This is a restricted atmosphere, high vacuum, it is a dry environment, no moisture content, and we know that from our experience that this high vacuum dry environment, here MOS2, it is one of the best material for giving one of the lowest value of friction. But when it comes to the question of practical use, normal use and field use, where we cannot maintain this low value of humidity, it is normal atmosphere. In that case, this MOS2 can show its weakness. That means, it will simply absorb moisture, and then from that oxygen will be active, and this sulphur will be attacked, and it will be actually S and O2, it will lead to sulphur oxide. So, oxygen will convert this sulphur into sulphur oxide, or it can go inside, it can also make molybdenum oxide. So, there are lot of investigation, there are lot of documentation in this particular subject. Whatever may be the thing, ultimately it is the total failure of the coating. So, what we like to say here, that just MOS2 alone, that can be good candidate for such high vacuum or dry environment, but for mass scale use in numerous mechanical application, this alone MOS2 cannot just serve as a good candidate and good coating material. So, that is why there has been lot of effort to formulate, to have a new formulation of this MOS2, and that is done by doping with some other material. That means, on one side we have MOS2, but another thing, it can be say titanium, chromium. So, these are the good candidates at for the literature, research literature. There had been also silver, for example, then lead also used, which may not be encouraged much, then gold. So, these are the candidates which has been tested, and here as per the literature search it is found that this titanium, chromium and also silver, they appear to be quite effective in that now this MOS2 with little addition of titanium, chromium or silver become more stable in high humidity and also with little rise of temperature. We know that from research document that MOS2, that is in open atmosphere, that is stable up to 400 degrees centigrade. So, when it is the requirement is above 400 degrees centigrade for any application of that component or part, then we have seen that this frictional coefficient it rises quite fast, and that means that is the end of the service life of the coating. So, this coating is no more useful. However, the whole idea here is also to have this titanium, chromium or silver with MOS2 to increase its capability to work at a higher temperature. And in this respect we can mention here that we have on one side MOS2, but also we have WS2, that is a addition, later addition, tungsten disulphide. So, this has a capability of holding its stability. It is chemically stable still up to 700 degrees centigrade. That can be also another good candidate, but it is to be also seen whether by adding such material in this side, whether we can also augment its property for various field of application, where still we have to work with a higher temperature or with a higher level of humidity. Whatever may be the case, now this coatings routine practice is to not just MOS2, but to have this doping of titanium with MOS2. So, the basic structure of the architecture of the coating, which was used with RF, that was just MOS2, and it is mostly a columnar structure. So, it is the substrate, this is the substrate, and on that we have MOS2 coating, and it is mostly RF sputtering with just conventional magnetron RF sputtering, but with the advent of this unbalanced UBM and CFUBM, it has opened up new opportunities and new scope of working with this MOS2, and in this case we can have a better architecture and we can blend this MOS2 with one material, say for example titanium. So, with this addition the architecture looks like and here we have MOS2 plus titanium. So, this titanium addition increases the capability of this coating, that has been also established, that with this addition of titanium this coating can work in an environment which is rich in moisture, water content, and the coefficient of friction is quite low, or even if we increase the temperature of the coating, still this one is better than this one. So, here also the pressure, that means the process pressure, that can be brought down compared to what is needed here, because it is now unbalanced magnetron or close fields unbalanced magnetron. So, with that we can bring high ion current on this side, and that is actually the case where we can work with still low value of the pressure, and according to this new structural diagram for this coating architecture, we can see that even with low pressure and low temperature, we can get a very good architecture of this coating, and then we have widened the scope of activity of this coating. So, this is one of the structure, but when we like to use this thing, we can also have the architecture like this. This is the substrate, and then obviously we have to have a sublayer of titanium, which is a adhesion layer. So, this is of titanium, and over that what we get? We get actually this MOS2 and titanium. This is actually MOS2 plus titanium. Now, during the sputtering, what one has to do, just to have a transition, first of all the routine process route has to be followed. That means, first of all cleaning this surface with titanium, then this titanium is used as the ion for cleaning this one, then changing the condition of sputtering. This titanium now should not be just used as for ion etching, but now this titanium should get deposited over the surface. So, the first step is cleaning this substrate surface with titanium, followed by deposition of titanium, and process parameter has to be monitored properly. And then according to the requirement, when we get this titanium sublayer, that means that is called the adhesion layer, then obviously the target for MOS2, that should be switched on, that should be activated, and here obviously it is the titanium cathode and MOS2 cathode. These are the two cathode, and for the reason, so this is you have titanium cathode current and MOS2 cathode current. So, this cathode current should be adjusted, and this should be. So, we have proper intermixing between titanium and MOS2 in this transition. So, it is gradually the titanium percentage is getting down and MOS2 percentage is going up, and finally, what is required in the coating, that is actually MOS2 plus titanium and that is the final content in titanium. So, once that transition is done, then we have a steady state deposition, and where keeping this titanium cathode current constant and MOS2 cathode current constant, this deposition can be continued for several hours to have a consistent bulk value of MOS2 and the bulk value of Ti content in this composite coating. So, this way one architecture can be built up. We can have another architecture, that is, say for example, it is also known that if this is the substrate, then over this substrate we can build a titanium nitride coating. There is no difficulty in getting a titanium nitride coating. So, titanium nitride by reactive sputtering, by using a DC or RF or pulse DC, that can be very well used. However, the whole idea here is to improve the performance of MOS2. We know that we call them super lubricious coating, but at the same time this MOS2 or WS2 we also call them soft coating. So, we have actually two extremities, ultra hard coating, hard coating, and this is soft coating. So, that is a wide range. On one side we have diamond CBN, those are ultra hard material. In between we have all hard material, that means conventional hard material, say for example, all carbide, nitride, boride of transitional element. We have aluminum, silicon, they are nitride or oxides, that can be also mentioned. However, on this side, on this extremity, we have a soft coating of MOS2 and tungsten disulfide. Now, this is going to be used on a steel whose surface property has to be improved a lot, and this surface property means it is the tribological surface property. So, this obviously our choice will be a super lubricious coating, which we have already mentioned. However, it is found that this coating can be also improved further. What we mean its performance, if we put a coating of titanium and if the deposition is done on titanium, that means this should be now the architecture. So, this is now the architecture, this is MOS2 plus titanium. So, it has been also seen that established from research document that a coating of MOS2 plus titanium directly deposited on a steel substrate, and a coating deposited on an intermediate layer of TIN. So, this architecture is better than a architecture only containing MOS2 and titanium. So, this way one can also design the architecture of the coating just to improve the performance, and here it is said that the load bearing capability of this coating is better and higher when it is put over a hard coating. So, a soft coating is well supported, well borne by one hard coating, and here the resistance to deformation is more, because when the load is applied on this side, there will be a tendency of deformation, since this substrate is of lower hardness. So, naturally whole thing will get deformed along with MOS2, but if we have a properly chosen architecture of a hard layer, hard metal like TIN, then it is expected that this coating will improve its performance. Now, this is one architecture, but it can be extended to this one. Say we have again a steel substrate, however, on this we can have titanium coating. This is a titanium nitride coating, and on this what we have, it is just not MOS2, it is just not MOS2, but here as we see here, say for example, this situation here it is actually co-deposition. So, this we should say it is a composite, it is a co-deposition, co-deposited coating. Similarly, now what we can do, instead of titanium, we change this titanium to titanium nitride. So, this top layer, now this top layer is going to be a MOS2 plus titanium nitride. So, in this case, what has been done, it is in principle MOS2 on which titanium is added to improve its property to stabilize this MOS2 coating, to stabilize 002 plane and so on. In this case, what we like to have TIN, that is one hard coating. So, on that we have put MOS2 TIN coating. So, if we consider alone, how will this performance will differ? Say this is just one TIN coating and substrate. So, we have now three architecture, one just with TIN, another with TIN, on the top of that we have MOS2 TI coating, and in another case we have TIN, on the top of that we have MOS2 plus TIN. And what we have already discussed, this is actually a coating which is having just what we have mentioned, this is actually MOS2 plus TI. So, whole idea here to maintain this lubricity, this remarkable lubricity of MOS2 over a longer period of time and in any atmosphere, in any practical environment. So, for that lot of architecture can be proposed and can be tested. Now, here what is the difference between these? So, here it is just on the substrate. So, compared to this we have a better load bearing capacity here. However, TIN is a better choice when it is the wear resistance and hardness is concerned. So, just to improve its lubricity or say coefficient of friction, in that case we are adding a top layer. But what is done here in this case, it is actually a TIN coating plus MOS2 plus TIN. Now, whether it is complementary to each other or supplementary to each other, that is the big question here, because it is something comes in support of the other, whether it is MOS2 that is going to help out TIN or it is rather it is the other way round. What we have to see here, the whole idea here to have what we call a hard coating and also lubricant and also having this lubricious property. So, it is also hard coating and also it is serving like a lubricant. Of course, it is solid lubricant. Now, all this MOS2, WS2, these are going to be a substitute for all sort of grease oil type of lubricant, and in most of the parts of machine, heavy machine tools, the parts are going to be coated with this MOS2 or similar material, and we must have suitable process to coat large parts, so that those machine can become also dry machine. So, dry machine means without having any application of oil or grease or any blend of that, but however, it will be just a dry part. So, there is no question of oil drop or grease coating. So, it is a solid lubrication. So, here what we find that we want both hardness and lubricant, because of the simple reason that when it is the question of wear resistance and with high sliding speed, high temperature and high load, in that case this coating from family of hard coating, that means the material from the family of hard coating, they are found to be very effective in that the wear resistance is excellent and remarkable. But when it comes to the question of very stable friction coefficient, even at a very low speed and at a high load, say for micro movements and other places, then it comes to the question of super lubricious material, which can maintain that condition of very smooth movement without any jerk, without any stick slip, and for that this MOS2 and similar materials are so useful and so effective. But here the idea would be, the whole idea would be not to just keep this use restricted only to slides guides, because mechanical component means it can be slider mechanism, slides guides, screw nut, it can be cam and follower, it can be the bush and the bearing, it can be gear and pinion, and so on. Wherever we find any sort of rubbing, it is only where we can pay attention just by putting this solid lubricant in the form of MOS2 and similar material. But say when it is the tool of production, say metal forming tool or metal cutting tools, in those cases also this material having this super lubricious property, that can be also have, that can also have one use, effective use, and that can be also attractive for those, and that is the idea behind here, to have this blending of this hard coating and lubricious coating, and that is why one can also call it as hard lube coating. So, it is actually hard coating and else the same time lubricating coating. So, this coating can be used for all sort of application like machining as a cutting tool, in all metal forming die, punches and similar areas, this can find extensive use. Now, the question that these are the architecture. Now, how we can rank this coating architecture? Now, for ranking this coating architecture, we have to find out some ways or means. That means, this coating has to undergo some kind of characterization, and it is going to be a mechanical sort of characterization. That means, the coating whatever we have mentioned here, that means just molybdenum disulphide without any support of TIN. We have a hard coating, a conventional hard coating TIN, and we have MOS2 with TIN support, and we have also MOS2 with a TIN support, and this is a composite coating. So, with that what we can find here, this hard loop coating for ranking, what we have to see here, this say hardness of the coating. Hardness of this coating, then adhesion strength, and then coefficient of friction. Okay. So, against this what we can see, that when it is the hardness, obviously that hardness of titanium, that will be the best out of that family. So, titanium will be the best, and it is also our experience that this titanium nitride plus MOS2 with a support of titanium nitride at the just beneath it. Okay, so, that beneath it, that is also another thing. So, that is actually the support, that is the second best. So, this is one thing. Now, when it is the coefficient of friction, and then what are the other coating, what we have mentioned hardness wise, this MOS2 titanium or MOS2 over this, these are not showing the same characteristics as that of this titanium nitride and MOS2 supported by this TIN. But when it is the coefficient of friction, obviously when it is the coefficient of friction, obviously a coating with MOS2 plus titanium, that will be the best one, because it is having high percentage of MOS2, and that gives the super lubricity, and it is better than this titanium MOS2, and titanium nitride is on the other side. However, if we like to consider both wear resistance and coefficient of friction, then the blend of this one with right blending between titanium nitride and MOS2, that would be one of the right choice in that direction, and accordingly that coating can be ranked as number 1 in this family, which can give a hard loop property, and this is means the hardness of the titanium nitride and also the lubricity of molybdenum disulphide. Another thing is also found out that this particular MOS2, this MOS2 is also assisting in refining the this grain structure, which is otherwise quite coarse, and that grain structure can be refined by this MOS2, and this way it is also playing another role, that refinement of this titanium nitride structure and thereby improving its property. So, from this we can see that this titanium nitride and MOS2, that can be one of the good candidate for all sort of application of coating, which require both wear resistance and also lubricity, and at the same time we have to also evaluate how good it is in terms of coefficient of friction, or wear resistance or hardness in comparison to MoS2 on one side, and another side is that titanium nitride. Okay. Titanium nitride. So, these are the few things one has to look. So, one has to look to this, and by this also what we can see that it is MoS2, but similar effort can be also made with other coating material, say for example, WS2 with some of the hard coating from this hard coating family, and it can be titanium nitride or chromium nitride or some of this. So, that can be also useful to augment this property. That means, it is the hardness at on one side and also the wear resistance on the other side. So, these are the coating architecture which are of immediate interest and immediate use, and these are the materials also need proper evaluation. That means, here comes the question of, once we are resolved that it is actually titanium nitride and MoS2, that is the combination, then we have to also find out what will be the percentage of this titanium nitride and molybdenum disulphide to get the best value of hardness, best value of grain size, best value of critical load for adhesion, and also the best value of coefficient of friction. Now, for this what we need to have here, actually the process parameter for depositing MoS2 and the process parameter for deposition of titanium nitride, and for that what we need, the cathode current for titanium, cathode current for MoS2, then the substrate bias, and process pressure. Keeping other thing constant, process pressure, keeping other thing constant means, if it is a pulse DC, then pulse frequency for the target and the substrate, that is not altered. So, with this one can find out the best combination of these two things to get one of the best value of hardness of the coating, adhesion of the coating, and low value of the coefficient of friction. So, with this we can make a summary of our today's discussion, that MoS2 and tungsten disulphide, these are the materials which are called super lubricious material because of their architecture, and this hexagonal array of this one set of molybdenum, that is in between two layers of sulphur. Now, molybdenum sulphur has a good bonding, but between the sulphur of adjacent layer the bond is weak, and that leads to a low value of friction, because the van der Waals force of friction, force of attraction is prevailing there. Now, what we have also seen that MoS2 coating can be augmented, its property can be improved, not just by use it alone, but by blending with the material like titanium, chromium, and sometimes also it has been found that material like silver, gold can also helps in getting low value of friction. The most important thing in the whole architecture is to have the basal plane orientation, that means this 002 plane of this whole structure, that should be parallel to the substrate surface. to have the lowest value of friction. It has been also seen that instead of this MOS2 or titanium, there can be a good blending of one hard component and one soft component, and with right blending and in the sputtering process, by controlling the process parameter, one can make a good composite coating, giving one of the very best value of coefficient of friction and one of the highest wear resistance.